here. And let's forget, I'm on a different computer. Okay, so the first discussion that we will kind of run into in this topic is one that we started when we were at the beginning of the previous chapter, when we introduced three different models that we could use to understand light. There's the wave model, the ray model, and the particle model. The particle model we're till the fourth unit of our class once we get some discussion of how electric and magnetic fields work. But the ray model, we got a little taste of at the beginning of our wave optics chapter. So the kind of determination that you would want to make if you were trying to determine whether or not it makes most sense to apply the wave model to a scenario you're trying to understand or the ray model. It's got to do with the relative size of the aperture compared to the wavelength of the light that's going through it. So in this case here, this doorway is physically much, much, much larger than the wavelength of any of the visible light that we are detecting in this image here. So that combination means that you're going to see essentially no interaction, or excuse me, no interference patterns when you look at the like the dark space that is being kind of intruded on by this light that's coming from outside. So in other words, we don't see any sort of like rings surrounding this image or this, I guess the bright spot that's projected onto the floor of this room. We don't see bright fringes surrounding it or dark fringes. We just see kind of a well-defined line where the light rays that are coming from outside are either making it through the door or they aren't. And in the case where the wavelength of the light source is closer to the aperture size, so in other words, when you have really small apertures, even though that they're not, you know, hundreds of nanometers in size, the way that light, that visible light's wavelength is, they're still, or the ratio is still a lot, I guess, closer to 1 for that scenario compared to what we see right here. So that's why it was easy to observe the interference patterns that we projected onto whiteboards last week for our week's lab, because the light that we were working with, a few hundred nanometers, was interacting with a diffraction grating that had spacing like somewhere on the order of 10 to the minus 6 meters. It would change based on which one you worked with in the first half of the lab. But the point is that we could very easily observe an interference pattern when the aperture or the slit spacing in that case was really small. So now we can kind of take a look at how to deal with large apertures. And this quantity here, I included on this slide. We talked about this last Wednesday, the like the crossover diameter, the point where the physical size of a circular aperture, or I suppose if you're working with a circular aperture and the physical size is somewhere on the order of a millimeter, it can get a little hazy as to whether the ray model is the best or the wave model is the best. However, this doorway here and all of the scenarios that we're going to be working with going forward, we're going to assume that they are much much larger than a millimeter, so that the ray model is the clear front runner in terms of which of these models is the appropriate one. So the ray model, as is stated here, instead of just kind of laying out some equations that describe how the ray model works, we're going to kind of make some observations or make some assumptions, lay some ground rules, in other words. So first off, I wanted to kind of bring this up here. We have seen these purple rays show up in the imagery from the textbook before now, but I just want to reiterate, it's not meant to imply that the wavelength of this light source is legitimately purple. In this chapter, we are more often than not going to be assuming that we're dealing with white light rays, which we understand to be the combination of a bunch of wavelengths put together. But in other words, unless we are kind of asked to investigate how that white light ray splits apart, its wavelength, or really its group of wavelengths, is not really important. We're just kind of concerned with where the light's going, whether it's passing from one material to another, or if it's interacting with some sort of matter that would cause it to reflect. So these straight lines are really like these arrows, almost like vectors, are light rays. And if you think back to the beginning of our not wave optics, but our superposition chapter, we saw a side-by-side comparison that showed or kind of demonstrated how waves can pass through one another without affecting one another in a way that particles can't. We saw like a side-by-side that showed like a pitching machine or a pair of pitching machines on one side and then a pair of loudspeakers on the other. So the rays that we're going to be talking about in this chapter are going to work similar to the waves that are produced by the loudspeakers in that old example. They can cross one another without affecting the other's speed, the other's wavelength, the other's frequency, any of that. In other words, they can't occupy the same point in space, or they can pass through the same point in space at the same time. So number 3, if we have a light ray that is not interacting with any matter, we can assume that it's going to continue traveling in the same direction that it started. It's not going to speed up or slow down. And unless there is some matter to kind of get in its way, we can assume that that ray is going to continue propagating forever. So in the case where there is some matter that gets in the light, the case is, I should say, when there is matter that gets in the light ray's way, what we would want to investigate is whether that light ray can actually pass the boundary between these two materials or these two indices of refraction, because we're going to resurrect that idea from chapter 20. Is that still chapter 20? No, it's the traveling waves chapter. I think it's 16 now in the new edition. But we're going to go back to that idea that we encountered a few chapters back. So we have these two materials. If the light ray is not actually capable of penetrating from material 1 to material 2, it's going to reflect off of this interface. So this is like what we saw when we were talking about the Michelson interferometer a couple of minutes ago. Specifically, if we applied it to either of the mirrors, well, there's the two-way mirror that's the beam splitter, but if we look at the other two mirrors that exist in the Michelson interferometer, the light that is coming from whatever source you're trying to measure is not capable of actually passing through that mirror. So it's going to undergo an interaction with the surface that will be either reflection or scattering. And these are two really similar physical phenomena. Reflection is like the more organized version of scattering. A light ray that is like working its way through material 1 but doesn't actually make it to the interface and still change its direction somehow is interacting with the particles that exist in material 1. So in other words, there's kind of an implicit assumption here that material 1 is not vacuum, that there's some type of material that, or some type of matter that this light ray down here that's scattering can interact with. However, the mechanism or the simple way that we can explain what reflection is and scattering is, they're pretty similar to one another. A light ray bounces off of something. And for reflection, we can generally think of this as like, not the, I guess, the more organized version of scattering. Whereas for scattering, this light ray does not, well, let me kind of phrase this clearly, because there are a couple of other differences between the scattering and the reflection examples that we have here. But imagine that there's some, let's say, gas particle, or to kind of relate this back to a demo that you might have seen before in an earlier physics class, if you have either like a fog machine, or if you go old school and you have like two dirty chalk erasers that you can clap together and put a lot of chalk dust into the air. If you shine a laser through there, you can see the beam of the laser in a manner that you don't see when you just shine it in the in air that's not loaded with particles that have small size. In other words, you didn't see the laser beams that we worked with last week. You could see where they landed on the screen, but you didn't see like a cylinder of light. So when there is material for this laser beam to interact with, and the material has to have like the right particle size, which is why we weren't able to see it in the lab last week, but this light ray can interact with that matter and change its direction. It's not going from one medium to the next, but it is changing its path. So the rest of these, and there's really a fifth light matter interaction that we can add to this. I'll bring this up before we go on to the next slide. But if we take a look at the light rays that actually are capable of passing through this interface, going from one material to the next, there is a change, or there's the possibility for the change in angle or like a bending of this light ray as opposed to a bouncing. Those terms are oversimplifications, but it's a good way that you can kind of get acquainted with the concept of reflection versus refraction if this is the first time that you're coming to it. So this light ray interacts with this boundary or this interface between these two materials, and instead of propagating at the same angle that it had before, now it's propagating at a slightly different angle. So the light ray is not changing its color, and it's not changing its like frequency, but what is changing is the speed. So if the speed of this light ray changes, but the frequency stays the same, the wavelength is going to be slightly different in material 2 as it is, or compared to what it would be in material 1. Now we have another example here where a light ray is incident on this interface at an angle that doesn't cause it to refract, and I'll say noticeably. So in other words, this refraction example is kind of an exaggeration. This absorption example is something that you can achieve if you were just to take like a laser pointer and aim it out of our lab. So you're inside, you point it outside. The laser pointer, or the light that the laser pointer is producing, that beam, is going to pass through the window without changing color. It's going to change speed as it goes from the air in our lab through the gas and then back into the air that's outside. But otherwise, its wavelength, its frequency, or its wavelength and its frequency, hold on, the frequency stays constant, but when the speed changes, the wavelength changes. So another thing that does happen in that scenario, specifically when you're going from air into glass, is that a portion of that light ray is going to be absorbed by the material. So in other words, you are still going to be able to see evidence of the light from the laser on the opposite side of the glass, but a portion of it's going to be absorbed. And it's kind of easy to overlook here, but the thickness of the ray changes a little bit so that there's some light loss. And that light that's lost is interacting with the matter, or I should say, maybe it's easier to say that there's like a cost when you send a light ray through different media. There's a certain amount of energy that you're not going to be able to get back. And that's not really the case for reflection because you're not actually sending it in one material or from one material to another. It's just all air or all vacuum. But when there is some crossing, I suppose, even in this kind of more idealized refraction example, a portion of that light is going to be absorbed. And depending on the properties of the second material and how its index relates to the first index, you can predict how much of this light will be absorbed. So kind of what's being communicated here with this dotted line is that for this example, there will come a point where you will not be able to see this light source anymore in material 2, so that it's being absorbed. You won't be able to kind of take this light ray and bounce it out, or bounce is probably the wrong term here, but pull it out into a third material if you wanted to. So we have reflection, refraction, scattering, absorption. I mentioned that there's a fifth interaction that we could kind of add to this diagram, and it is transmission. I used that term a little bit earlier. In the case of refraction and absorption, some of this light is going from material 1 to material 2. So it's transmitting this boundary, it's penetrating, and it's not actually being forced to reflect back into material 1. So transmission is not really it's, you could group refraction and absorption underneath an umbrella labeled transmission. They're both examples of that. So that's our long-winded third observation. Now, fourth, this is more of a function of how we're going to start problem solving and trying to understand how these light rays interact with the matter that each one of us can see in our rooms right now. So an object, or this term, is going to be the source of light rays, and the object, there are a couple of different ways that you could think about this. It can be either self-luminous, so something that's producing its own radiant energy, like the sun, a star. It could be the filament of a light bulb, all of those scenarios. But for everything that you can see in your room right now that isn't glowing, that's not producing its own light, you are seeing some form of reflection or scattering, really. So the pine tree here that we see on the right-hand side, that's going to be a kind of common object that the imagery in our textbook uses. This tree is not producing its own light, but if it is, let's say if sunlight is incident on this pine tree, we can treat every single location on the pine tree as if it's a like a source of diverging light rays. So in other words, the tree is not producing its own light, but when it interacts with sunlight, it's going to do so in a manner that's going to cause light rays to move outward in all directions. So we're specifically here not talking about transmission, the light's not passing through the tree, but for the stuff that is either, well, that's undergoing some combination of reflection and scattering, we can assume that these light rays are going to go outward in all directions. So maybe a less clunky way to say that is, if you were looking at something that's in the room with you right now, and you slightly changed your position, you wouldn't be able to find a position where none of the light rays coming from your lamp or whatever interact with that object. You wouldn't be able to find a position where that object becomes invisible. And that's because the light rays that are interacting with that object are moving outwards in all directions. So every potential line of sight is covered by that diverging bundle of light rays. The flip side, if we were concerning ourselves with, let's say, the light rays that are coming from the sun and have not yet interacted with this pine tree, for objects that are sufficiently far away, it's okay to assume that the light rays are going to arrive as a parallel bundle like this. So in other words, they are, well, all parallel to one another. They have not yet started to diverge. That's the kind of the important distinction here. So this here, 5, the eye sees by focusing a diverging bundle of rays. There's a diagram that kind of shows the short story or the simple explanation of how light can interact with material outside of our eye, then pass through the natural lens that exists in our eye and form an image on our retina as opposed to a screen that our brain can then interpret. The same thing happens with this simple device. This is called a camera obscura. It is the same basic design as the earliest film cameras, or even before film. If you're familiar with what's the term? I think daguerreotype. It's like a essentially like a photograph that you could make on a, or like an image that you could capture on a thin metal sheet, kind of similar to the way that we thought about like older Polaroid cameras. You needed an aperture so that you could collect the light rays that you do want to be a part of your image and kind of cancel out all the ones that you don't want to be a part of your image. And in the case of the camera obscura, this is something that you could legitimately achieve if you had a dark room with like a small aperture. So any object that's outside of that room, and one that's aligned so that rays can actually go from the tree through the aperture, it's going to be capable of producing an image on the far wall. The room's got to be dark so that you can basically, so that you know that the light that you are viewing in the room is not coming from any other source but the object that's outside. And if we take a look at this diagram down here at the bottom, you can see how some of these diverging light rays that come from the top of the tree and the trunk, so or I suppose the bottom or maybe the stump, that's what we would need in order to, I guess, capture the entire image of the tree, if that makes sense. All the other points in between are doing exactly the same thing, but the bare minimum that we need to kind of make sense of this is the top and the bottom of the image. So some of these light rays make it through, most of them don't. And the ones that are coming from an interaction at the lower end of the tree, they're going to end up on the higher portion of the wall and vice versa for the upper portion of the tree. So we can find a ratio or a relationship between the height of the actual object and the height of the image that forms upside down, because this simple camera obscura without like an additional lens to invert this image is going to make an upside down version of whatever is outside. So HO for the height of the object, and DO, that's the distance from the object to the aperture. We can make a ratio between those, and HI, the height of the object, and the distance between the aperture and the object, the height of the image, and the distance between the aperture and the image. And we can relate this camera obscura to the human eye. Sorry, I did not realize that I had anything audible here. Okay, sorry about that. The difference here, or there are other obvious differences between just a camera obscura and the human eye. But in addition to the fact that there is a lens here that is causing these light rays to converge on the surface of the human, or inside the human eye, the surface that this object is going to be projected onto is not just a flat wall like the camera obscura, but instead is the retina, which is curved. So we're not going to spend a ton of time talking about like the biology that kind of underpins how this natural lens forms and how like the optic nerve makes sense of the images that show up on the retina, but we can relate it back to this simple concept here. And we're also going to be, well, this week's lab is going to involve one experiment that's kind of like splitting the difference between the camera obscura down here at the bottom and then seeing how you can take diverging light rays and cause them to converge by using a lens. Okay, so going back to those four interactions with between light and matter, reflection and refraction are going to be the ones that we spend the most of our time on. Absorption and scattering, those are, you can kind of think about each of those as being a subtopic, where scattering is like a subtopic to reflection, absorption is going to be a subtopic to refraction. So we're going to kind of cut that in half and cut this discussion into halves, essentially. And we'll start with reflection. So the law of reflection is something that we can form by taking a closer look at that, that light matter interaction diagram that we saw a few slides back, and trying to understand what happens when you have more than just one light ray that's interacting with some reflective surface. So we can assume that this reflective surface is an ideal mirror so that like none of the light can actually transmit. It's all going to be forced to bend or to change its path when it interacts with this reflective surface. So we can kind of split this ray, or we can split this process into halves, like a before and an after, so that if we were just to take like an edge-on view of the same scenario, the incident ray is the light ray before it's interacted with the reflective surface. The reflected ray is obviously the light ray after it has interacted with the surface. And the value here for the angle of incidence, theta I, that determines what theta R will be, so long as the mirror is plane. And that, I mean, PLANE for flat. This is something that you can also confirm for mirrors that are curved, but I guess we can think of our plane mirror as the idealized case here, the one that is kind of the easiest to evaluate. So this angle of incidence, this is always measured from a normal. Sometimes you'll hear, I'm sure sometimes I'll say the term surface normal because you are always drawing this dotted line with respect to the reflective surface. And normal has the same meaning here that we encountered in semester 1 when we were talking about normal forces. Don't think of it as the opposite of weird, but just it indicates that there's a 90-degree angle between where you place the normal and the section of the mirror where the light ray is interacting with it. And I should note that this incident ray is not physically different than the reflected ray. It's the same ray. We're just kind of breaking it into a before and after. So whatever the value of theta I is, theta r will be the same. So theta I is equal to theta r. That's essentially the mathematical version of the law of reflection. When we get to this week's lab, I'll reiterate when we're in the lab as well, but I just want to kind of plant the seed now. You are never interested in the angle between the surface of the mirror and the incident ray, or the surface of the mirror and the reflected ray. It's always got to be measured with respect to some normal value. Even though if we were to take 90 degrees and subtract whatever theta I is, this complementary angle on the other side is going to be the same value. So I guess this is more about making the law of reflection consistent with the law of refraction, or Snell's law, like we're going to see in a moment. So in this case here, it almost kind of seems like an afterthought, but it's important to remember to measure these angles of either incidence or reflection with respect to the normal, never from the mirror surface up. So I mentioned that we can sort of think about scattering as a disorganized version of reflection. You can think of diffuse reflection as almost a middle ground. And let me roll backward here because I don't think I used the term. Yeah, I overlooked the term specular reflection here. Think of specular reflection as being the most organized type. So now diffuse reflection is what you get when you have a reflective surface that is not perfectly planar. So imagine what happens when water or when light reflects off of the surface of a pond that's got like some waves passing through it. You're not guaranteed that the vertical position of every section or every like parcel or drop of water is going to be the same as all the others around it. However, you can still show that the law of reflection is still valid here. We've got a bunch of light rays that are interacting with this surface, or they're coming from some source as parallel bundles, but when they interact with different parts of the surface, they're going to reflect at different angles. So for each of these individual rays, theta I and theta R are guaranteed to be the same, but the positions of the normals will not be the same for all sections. If we were to take like this first ray that's all the way to the left, if we were going to draw the normal, it would be perpendicular with respect to this one section of the surface. So it wouldn't go straight up, it would go straight up or it would go up into the left instead, because we're not like looking at a flat section, kind of like the one that's this light ray that's here at about the midpoint of this image. Meanwhile, if we were to choose one of the light rays here that's like in the last third, since this part of the surface is kind of sloping down and toward the right, the normal that we would draw would be up and to the right. So the individual theta R values are not going to be the same as any other theta R value. So to say that another way, even the angles of incidence are going to be different just based on the nature of the surface that the light ray is interacting with. But for each of these individual rays, theta I and theta R will still be the same value. You're just ending up with an image that would form or like a reflection that's less organized than the specular reflection example that we assumed when we were looking at the plane mirror on the previous slide. Let me pop. Okay, it looks like we're still doing okay in the chat. Does anyone have any questions that they want to ask on mic? Because I've been going for quite a while here. Okay, you can interrupt me at any time if you do have questions. Let's keep going. So this slide here kind of walks us through how we can use ray tracing to determine where an image shows up where it does, or kind of in this case here, why an image shows up where it does, because we've all got experience looking at a flat mirror at ourselves and then seeing an image of ourselves that seems to be behind the mirror. We know that the mirror is reflective but opaque. So the light rays are not actually going through the mirror. There is an interaction between the object. Imagine that like you're wearing a hat or something that is above your eye. You're standing looking in a flat mirror and you see the image of that hat. So about the same height away from, or not about, but literally the same height away from the image of your eye as what you would measure if you had a meter stick and went from the eye to the top of your hat. However, the human eye has got a natural lens that causes these light rays to converge or to bend inward as the light rays refract with this material. So if we were to take a look at the object, so this is the hat that's on your head, and measure the distance between that and the actual surface of the mirror, the image of the hat should look like it's the same distance behind the mirror. So this is the first time that we have an S and an S prime. We saw with the camera obscura essentially the same quantities, but they were called D0 and DI for the object distance and the image distance. Here, the object distance is our S, the image distance is S prime. So P prime would be the image of the hat that's on top of your head. So we understand that what's actually happening with these light rays is that they're being produced by, let's say, the light that's in the room with you in the mirror. Let's say that you're looking into a bathroom mirror, so you probably have an overhead light in that scenario. So light rays are coming from that source. They are interacting with the hat that's on top of your head, and they're diverging. So the light rays that are diverging like toward your back are not important to this conversation. That's why we're only seeing a small portion of the diverging bundle of light rays, but they're going to interact with this surface. If we were to draw normals for each of the three example rays that we have here, we would find that theta I and theta R are the same value. They are going to, so after reflection, they're going to kind of be fed back toward this aperture, like the pupil that lets light get to the lens that's on the interior. And once those light rays start to pass through the lens, they pull inward. So they do the opposite of what's happening here. They converge as opposed to diverging. What we can do, though, is take these actual reflected rays and then trace them backward so that they become, instead of real rays that are actually moving through this section or this side of the room that you're imagining you're in, they become virtual rays on the opposite side. So they're not really going through the mirror, but they look as if they are diverging from some point behind the mirror. I've got some stuff to unveil here. And this expression down here at the bottom is really just the law of reflection, but stated in terms of distances as opposed to angles. So since theta I and theta R are equal for each of the three light rays that we see diverging from the object P, they are going to appear to diverge from a point that's the same distance behind, or the same distance into the mirror. So the object, I should say the image distance, is going to be equal to the object distance. Now, maybe a hat was a bad choice for the example. Maybe you could just imagine that you've got, let's say there's a zit that you're staring at in the mirror. It is just in one position, it's not an extended object. So for the hat, it is an extended object. It doesn't just have one vertical position, but it's made up of a bunch of different vertical positions stacked together. So the way that we would adapt that process that we saw for the single point source so that it can accommodate objects that have height is to just take essentially one sample of the diverging light rays that are interacting with the top of the object, one sample that represents the diverging light rays interacting with the bottom, and we can basically apply that same law of reflection just twice. So we've got these purple rays that just represent the top of the tree. So they are going to appear to diverge from a point that lies some distance SP behind the surface of the mirror. And then we can essentially confirm that the same thing has to be happening for the bottom of the tree and also all the points that are in between. So this would become pretty difficult to understand if we had all of the points that make up or that lie in between P and Q represented in this ray tracing diagram, but they do exist. That's why you wouldn't just see like the bottom. Let's imagine you have a top hat on because you're looking at your pimple in the fanciest way possible. So the brim of your hat would be like Q, the top would be like P. So you would still be able to see all of the points in between the brim and the top is my point here. And if we trace the the reflected rays back to the point where they appear to be diverging from behind the mirror, we can essentially see exactly the same thing as we saw a bit earlier with the camera obscura. It's just happening down here. So you have a lot of these diverging light rays that are coming from the top of the tree that don't make it into your pupil, a bunch that are coming from the bottom that don't make it in. But the result is that you end up with a smaller inverted image of whatever object you're looking at. So the tree in this case, it could be the hat in the other case. So there's more, well, to backtrack a little bit here, ray tracing with flat mirrors is pretty much always going to be this straightforward. Later on in the chapter, we're going to encounter curved mirrors and ray tracing with lenses. So we're overlooking a whole bunch of stuff that we're going to expand on here as far as what's going on with this converging lens. But for the most part, the law of reflection is that simple. You're either measuring an angle and comparing it to another angle to confirm that they're the same, or you're measuring a distance to compare to another distance to confirm that they're the same. There's a bit more when we talk about what happens when these light rays actually go from one material to another, or they interact with a boundary or an interface. And that's what's being indicated here by this diagram. So what you don't see is a light source off to the left. This looks like it is, instead of a laser pointer or something that just produces light in one or at one wavelength, imagine that this is just like an ordinary incandescent bulb that's got a slit card on it, so that instead of getting all of the light that's spreading away from this bulb, you can just isolate one narrow bit of it. So that is implied to be on the left side here, and it's interacting with this prism. And the prism has got an index of refraction that is greater than any of the air around it. It pretty much has to, if this is something that you're going to achieve in like a real life lab scenario. So this light ray, once it interacts with this boundary, some of it is going to reflect off, just like we encountered in the previous handful of slides talking about reflection. So we could sketch a normal that's perpendicular to this face of the prism and measure a theta I and a theta R and demonstrate that they're the same value. However, most of the light is passing through that boundary. Only some of it is actually reflecting. So more light is transmitting than reflecting for this first interaction at this first boundary. And we can kind of see clearly that the path of this light section here is very different than the path of the ray before it actually passed into the second medium. So there's bending that's happening. The bending happens right here at the interface. And if we continue onward to this far face of the prism, we see essentially the same event happening in reverse. So we have this essentially horizontal beam of light that strikes the surface of this prism and it gets bent downward and toward the right. but now the face or the interface of this side of the prism is like at a different position on this plane, but the air that's surrounding the prism all has the same index of refraction. So you go from horizontal to slanted, but now as that light's going from the prism back into the air in the lab, it's going to go back to horizontal. Now, if you look closer at this interface here, just as we saw before, not all of the light is transmitting across that boundary. Some of it is bouncing back through the body of the prism. So there's some degree of internal reflection happening here. We're going to look at the the criteria for total internal reflection coming up a bit later. So that's what happens when none of this light actually makes it out of the prism and back into the air, but it all reflects back through the body of the prism. Tracing the part that reflects on the interior of the prism, it's going to interact with this interface. And again, you're going to have some portion that reflects and then some greater portion that refracts back outward. And again, it's not a coincidence that this reflected ray is parallel to this refracted ray after the, what I guess that would be, this is the third interaction between this, this light ray and the boundary between the air and the prism. And then there's a little bit here that is going to reflect off of this face and make its way out of the prism. So we're seeing the law of reflection happening most prominently in this case here, but it's also happening on the interior of the prism. And then the rest of it, so the rest of this light ray that has split up at this first interaction, the rest of it is going to transmit. And we could, trace even more. So there's another instance of transmission happening here, another instance of reflection happening here. Then I can call this ray transmission, and this is another example of reflection. But we're losing intensity for each additional interaction. So in other words, the intensity of this portion, maybe I'll choose this one here, this portion that refracts across this surface and bends is a lot less intense or less energetic than our original before it split up at all. So I mentioned that with the law of reflection, if you have a light ray that's just confined to one material and it's interacting with either a boundary between two media, or if it's just an ordinary plane mirror, the angle that you would measure from the surface of the mirror up to the ray and from the surface of the mirror up to the reflected ray, those are going to be the same. But the reason why we want to kind of get acquainted with measuring from the normal down to the ray in each of these cases has to do with Snell's law here. So we're changing subscripts a little bit. Instead of theta I and theta R for incident and reflected, we have theta 1 and theta 2, where theta 1 is going to be the incident or the angle of incidence here because our light source is starting in material 1 and going toward this boundary between media. And then theta 2 is going to be the refracted ray inside of the second material. Now, it wouldn't be wrong to call this weakly reflected ray theta R, but it just gets a little bit tricky because theta R could potentially apply to either reflection or refraction. So the 1 and the 2 kind of helps you connect an angle to a medium. And we can take it a step further and connect the angle, the medium, the speed, and the wavelength, because the frequency is staying constant. So if the index, if N2 and N1 are different values, the light ray is either going to speed up or slow down based on which side it originates from. And the wavelength is going to have to change in response to that. So anyway, we've got our normal now that extends beyond just the point where the light ray interacts with the surface. And I've got an angle of incidence theta 1 that is greater than theta 2. That is going to be the case whenever the second medium has a larger index of refraction than the first one. So this is like what you would see if you had a laser going from, let's say, the air in a lab into glass or into water. We can use Snell's law here to relate the product of the sine of an angle and the index that matches up with where the ray is at that point in time. So that n1 sine theta 1 is equal to n2 sine theta 2. We're assuming here that n2 is greater than n1. We would see the opposite if instead the higher index material was where the ray originated and it was refracting, into a lower index material. I believe, yeah, that's what's happening here. So they haven't changed theta 1 and theta 2 so that they still match up with medium 1 and medium 2. But imagine that instead you take your light source and let's say you have a laser that you submerge in water and you want to see how that beam is going to refract as it goes from water back into air. Since you're going from a large n to a smaller n, the later angle, which would still be our theta 1 because it's in medium 1, is going to be the larger of the two. And take a look at this image from the previous slide compared to this one here. They are the same, aside from the directions of these rays. So the weak reflected ray is going to be confined to medium 1 in this example, but since the light source is starting in medium 2 this time, the reflected ray is also going to be in medium 2. But the angles, theta 1 and theta 2, would be the same, assuming that this medium 2, or that medium 1 and 2 are the same in each of these cases. And I know we've encountered this in our traveling waves chapter, but I just want to point it out one more time. The imagery from our textbook always assumes that the shaded medium is the one that's got the larger n value. Okay, we've got an example here. I'm at 29%, so this is something we can work with. A ray of light moves through water and strikes the surface of a transparent block at an angle of 27 degrees. What is the refracted angle? Theta 2. So let's take a crack at this. I'll log in here, and we can solve this one in real time. Okay. All right, give me a second. Okay, there we go. Okay, as soon as I'm able, I'm going to start sharing on this side. Let's go to OneNote. And we'll look at example 34.1. So here is our scenario. We want to use the law of refraction or Snell's law. Those are different names for the same thing. We know that the index of refraction for material 1 is 1.33. So I'm going to just kind of reiterate here that this is going to be material 1. The other side is going to be material 2. We want the refracted angle. So this is kind of the longest possible version of a single interface Snell's law problem. We have n1 times sine theta 1 being equal to n2 sine theta 2. We're looking for our theta 2 here. So our first move should be to divide both sides by n2. So we can get sine theta 2 by itself on one side. let's plug in what we know. 1.33 times the sine of 27 degrees. We can divide that by the index of refraction for the second material. So there's a huge hint or a clue here just in the diagram. It's not to scale, but we can kind of see that theta 2 is smaller than theta 1, and we can confirm that it should be because 1.79 is greater than 1.33. So let's do this calculation. And let's make sure that we are in degree, especially if you were working on wave optics previous to this. So 1.33 times the sine of 27, that numerator is going to be about 0.6038 divided by 1.79. If that is, hold on, this is the sine of theta 2. Our last step is to take the arcsine of both sides. So theta 2 7.9. Let's see. So we get 19.71 for theta 2. We are back in degrees, and we have 2 sig figs, so we're going to make this 20. Here's our theta 2. Okay, so anytime you know 2 indices of refraction and you're trying to find an angle, it's essentially like one step longer because you are at first calculating the sine of some angle and you want to figure out the angle by taking the inverse sine. However, if you have 2 angles and you're solving for an index of refraction, that procedure is going to essentially be one step shorter because you don't have to take an inverse sine. You just can rearrange this to solve for either n1 or n2. Let's see. Okay, so next up, we've got some discussion of how wavelength is impacted here. So I'm going to stop sharing on this side. I'll actually log out just for bandwidth reasons. And then we can pick up again over here. Okay, so we confirm that this angle goes from about 27 to about 20 degrees because of the ratio between these indices of refraction. Now, we know that the frequency is what's staying the same here. So this is kind of like something that, let's see, did we have a direct corollary to this in either of our first 2 labs? Not exactly, but this is conceptually kind of similar to the last problem on our traveling waves lab, where we imagined that we were in one lab with air that had a consistent temperature, but you had 2 different tuning forks. They had frequencies that were different by a factor of 2. And we found that they would propagate at the same speed, but the one with the higher frequency would have to have the shorter wavelength as sort of a compensation. So V and lambda, or V not changing, but F changing, means that lambda has to change. In this case here, V is changing because this light ray is going to travel slower when it's in the higher index material. So in order to keep the frequency consistent, the change has to be reflected in the wavelength. And this image down here at the bottom is one that we saw in chapter, the traveling waves chapter, I think the second half, if memory serves. Here we had just a single light ray, or a wave in this case, that was going from one material to another. So you have an index of 1 to something bigger than 1, and then back to 1. And we saw that the wavelength had to change in order to accommodate that. So if you're going from a low index material to a higher index material, we know that the angle is going to go from large to small, and the wavelength is actually also going to go from large to small. And then on the opposite side of this boundary, if you're going from small to large, we know that the angle should go from small to large, and the wavelength itself is also going to go from narrower to wider. It's a little harder to see on the second interface, but since we're assuming that we have vacuum on either side, lambda vacuum that is indicated here on the left would be exactly the same as the value that you would see on the right-hand side. So if we take a look at what has to be going on with the angles here, so kind of incorporating what we already knew about the index of refraction and how it relates to the speed of a light wave. If we can relate that to Snell's law, here we've got a parallel bundle of light rays that are incident on this surface here. They don't strike at the same physical location on the surface because they can't. They're parallel, they're not literally overlapping one another. So we have two different normals that we would want to, or that we would need to sketch. This first one for the lower ray, if we were to take, or we could extend this normal back up into like material 1 and measure what the angle of incidence would be, but it's going to be exactly the same as the one that's indicated for the upper light ray. So in other words, we can kind of make an argument that if the normal is perpendicular to the interface, then whatever value I would measure down from the normal to the lower incident ray has to be the same as what you would measure for the second one, the higher incident ray. So what's kind of important here is the pair of right triangles that we can make by connecting the two normals to one another, where again, that normal is going to, or the distance between those 2 points is going to depend on the parallel bundle of light rays that you're working with, and then whatever the angle theta 1 would be for that parallel bundle. So in this case here, we know that we've got a perpendicular or 90-degree angle right here. We have an angle here that's got to be the same as your angle of incidence. Again, we just have a surface, two parallel lines. We can show that those angles need to be the same. So the angle that is left is going to be 90 degrees minus whatever the incidence angle is, but that is not the refracted angle theta 2 that we care about. We'd have to go into the second material to find the refracted angle. So that would be this one here. So this is our theta 2. We can find it by looking at the normal for the lower ray. It's got to be exactly the same as the one that we would measure if we extended this normal for the upper ray into material 2. So we have two right triangles that share a hypotenuse, but their legs have different values. I'm sorry, I did not mean to click there. The only way that you can achieve this, or the only way that you can kind of make sense of how the speed is changing but the frequency is not, is to evaluate the wavelengths both before and after. So if we're assuming that both of these light rays are coming from the same source, this lambda 1 is going to be the same for the upper light ray and the lower one, but lambda 2 is going to be the affected one. So lambda 2 is the wavelength after the light ray has actually passed the boundary and it's refracted. So it almost looks like the lambda 1 and lambda 2 are measuring lengths here, and that's not really the case. It's only the wavelengths that you would be able to extract if you instead of just looking at like the geometry of the scenario up here at the top, if we look at what's happening to the wavelength, we would see that the wavelength lambda 2 would have to be smaller than lambda 1. So here we have our first thought question for this chapter. A light ray travels from medium 1 to medium 3 as shown. We want to figure out how we could compare the index of refraction to medium 1 or for medium 1 to medium 3. And I can tell you that D is not correct. You can make a judgment about how 1 and 3 relate to one another without knowing a numerical value for 2. But take a second to see if you can work out which of these should be the correct answer, and then we'll talk it through like we normally do. Okay, so let's look at the first interface. We have material 1 and material 2. Our incident ray is, or excuse me, our angle of incidence is 20 degrees. The refracted angle is 30. So we go from small to big. That tells us for sure that N1 is greater than whatever N2 is. So now if we look at our second interface, we have a refracted angle of 30 degrees. That's going to be the same as the incidence angle for the second interaction. So you go from 30 degrees to 10. So from big to small. We know that N3 is bigger than N2. So we have a way to compare N1 and N1 to N2 and N3 to N2. That's why we can eliminate D right off the bat. We don't need to know exactly what the number is to know how they compare to one another. So we have a 10-degree increase for the first interface, a 20-degree decrease for the second. So again, we can eliminate A because they're not the same amount of either increase or decrease. So you know that N1 and N3 are not the same. So that leaves us with B or C. Either N3 is greater than N1 or N3 is less than N1. And N3 would have to be greater because of the fact that there's a 20-degree loss for this interaction compared to a 10-degree gain. So in other words, material 3 is slowing light down more effectively than material 1 does. So that means that the index of refraction has got to be greater for material 3. Okay, so this next topic here kind of relates back to the diagram that we saw a few slides earlier. Let me see if we can jump back here. So when we looked at this slide, we were able to find instances of reflection and refraction, and but not total internal reflection. So in other words, this interface right here, some of the light ray reflects back into the prism, but most of it doesn't. There are conditions where you can create a scenario where a light ray does reflect completely on the, or totally on the interior of a prism. And this example comes right out of the book, obviously, but it kind of walks us through determining what the index of refraction for a material is, and then using that to predict what the critical angle should be. So the angle beyond which all of the light that you send into the prism will reflect back into it, and none of it will refract out. So here we've got a prism that is a 30, 60, 90 triangular prism. A laser beam's incident on this left leg of the right triangle, and it's not sketched out here in the little diagram, but if we were to draw a normal for this face of the prism and then line up the laser beam so that we could determine what the angle of incidence would be, we would get a 0 degrees because the laser beam is perpendicular to the surface, just like the normal is. So for this scenario, it doesn't really matter what the index of refraction is for this specific material. The laser beam's not going to deviate just because the sign of 0 is also 0. So the interesting stuff happens on this second boundary. So the index of refraction now, we can call this N1 because this is where like the magic is going to happen. There's nothing interesting happening on this first interface, but the second one here. So we can call this our incidence angle. And now it's not going to be 0 because I'm drawing the normal relative to the hypotenuse, not to this vertical line. So that is indicated here in our little diagram. We've got, so our normal is here. The angle between the horizontal and where our normal is going to be this phi value. So, excuse me, not phi, but that's going to be our refracted angle. So we're calling this theta 1 here because we're saying that the air in the lab is going to be material 1. So N2, no, that's not the way that they have it labeled here. Okay, I'm sorry. So N1 is still going to be the index of refraction for the material. N2 is going to be air. So this is essentially 1.00. In reality, it's like 1.0007 or something like that, but it's normally okay to round down to 1. If we can measure this angle here between the horizontal and not the normal, but where the light ray actually emerges, we have 22.6 degrees. So that is not the angle of refraction by itself. We would want to go from the ray that emerges to the normal, not just relative to the horizontal. So that's where we get this unknown theta1 value and our phi value. We want to kind of combine those to figure out what our theta2 has to be. So here's the same image, but with some new text up top. We're trying to solve for N1, and we know N2 is just going to be air. Theta2 is going to be our theta1 value added to that phi. And again, we can make a kind of simple argument that if this interior angle is 30 degrees, then on the opposite side of this interface, theta1 also has to be 30. So that's where we're getting 52.6 degrees. We can divide that by the sine of 30, we get 1.59. So this is the index of refraction for the material that makes up the prism. It makes sense that this value is larger than 1 because we went from a 30-degree angle to now this phi value here, 22.6 degrees. So we went from big to small. Now, if we had a prism that was made of exactly the same material, but instead of being a 30, 60, 90 right triangle, we have a 45, 45, 90 right triangle. Just changing the dimensions of this triangular prism would, and leaving the incidence angle exactly the same, that would be enough to go from a scenario where some of this reflects out, I should back up here, where some reflects out, some of it's, I should say some reflects inward, most of it's going to refract out. Here, now we're going to be able to kind of evaluate what would happen if we had a prism that had slightly different dimensions, but was made out of the same material. So here, again, we've got an incidence angle of 0 degrees for this interface. So we can just kind of extend this in here. It's not going to deviate at all. At this point here now, we are going to draw a new normal. So the one that is kind of pointing toward the upper right of your screen, that's the surface normal for the hypotenuse. And then the horizontal dotted line is just there for a guide. So we can make an argument here that if this upper angle is 45 degrees, and we know that this is a 90, this interior angle at the lower side also needs to be 45, which means that the one below it is also going to be 45. And most importantly, the one on the opposite side is going to be 45. So sine theta2 is going to be 1.59, so something that's bigger than 1 times the sine of 45 degrees. If we're solving for theta2, we're going to have something that is greater than 1 again. So this is not going to yield a real or like a meaningful angle theta2 because you can't take the sine of something, or the inverse sine of something that's greater than 1. So what we have determined here is that the scenario on that previous slide would not allow any of the light to refract out of the prism into the air. Instead, it would all be captured inside of the prism itself. And this is what's indicated here. So clearly these are different wavelengths, but they are mostly just kind of color-coded so that you can tell which light ray is doing what. The impact that the difference in wavelength has here is, it's not 0, it exists, but it's negligible for this part of the conversation. There's a later conversation that'll let us dig deeper into why these don't all refract at the same, to the same angle. But let's take a look at our blue example where you have an interface here that's slanted so that the blue is going to reflect some of its light right off of this face. Most of it's going to refract so that we can kind of clearly see that the light ray has bent here at the interface. It's going to hit this interface here and reflect inward. So no part of that light ray refracted out after this second contact. Meanwhile, for the yellow and the red, we have a case here with the yellow where it's going to refract. It bends visibly here, and it does bend a little here. It's kind of hard to see, but it doesn't maintain exactly the same angle. It bends a bit there. For red, now it is hitting this angle, or excuse me, hitting this face. It's refracting inward. There's like a teeny tiny bit of this red ray that's reflecting outward, but most of it is refracting in. And once it gets to this this face here, it's gonna refract outward. But the blue ray here is the one that's not capable of bending back out into the air. And that's just because of the index of refraction, or the combination of the index of refraction of this material, the incidence angle, and what the refracted angle would have to be if it were to emerge. So as long as you are dealing with a prism that's surrounded by air, you can determine what this critical angle theta c is by just taking the inverse sine of 1 divided by whatever your index of refraction is. If you were instead conducting this experiment underwater or submerged in any other material, you would change the numerator here. But unless a problem indicates that, it's safe to assume that you're dealing with air. So for this scenario here, I didn't realize that I didn't actually solve this. So for our 45, 45, 90 right triangle that's made up of a material that has an index of refraction of 1.59, you would end up with about 39 degrees as the critical angle. So this diagram here kind of shows the all the points in between the case where all of the light is refracted and none of it is reflected, and then on the opposite side where none is refracted, all is reflected. Imagine you've got some object here that is in some material N1, it's shaded, so that's telling us that N2 is going to be less than N1. For a light ray that is incident on this boundary with a 0 degree or a 90-degree angle with the boundary, a 0-degree angle with the normal, all of it is going to transmit. It's all going to pass through. It's not going to bend at all. Then as you work your way toward the left, as these angles of incidence are getting larger in magnitude, part of the light ray is going to reflect back through the material that makes up N1. Most of it will refract out, but that increases, or I should say that the tips or the scales tip more toward reflection the greater this angle gets. And there's a turning point right here. So this is when the critical angle is, or I should say the angle of incidence is equal to the critical angle. You're going to have this point here where most of it's going to reflect back through the boundary or through the material that makes up N1. The rest of it is going to reflect parallel to the surface. So in other words, the refracted angle would be equivalent to 90 degrees, which is what's being kind of communicated right here. We have a new normal for this intersection point, but the refracted ray never fully makes it into material 2. It just lies along this boundary. So here's your turning point. As soon as you exceed that angle of incidence, none of the light is going to be capable of refracting out. It is all going to reflect inward. So this is something that you can exploit and apply to a few like real life scenarios. This is like a basic ray tracing diagram for a pair of binoculars. You have a couple of converging lenses that we're going to talk about some more later. Imagine that you are using this to view some object that's so far away that the light rays that are coming from that object toward you are essentially parallel. The moon would be a perfect example of this. So the converging lenses do the job of causing these parallel light rays to start bending inward. But instead of just trying to focus them at some point on the interior so that these slightly thicker eyepiece lenses can turn it back into a parallel light source, you can stack or like pack the interior of your binoculars with prisms for which you can guarantee that the angles of incidence for the second the second contact here, this being the first contact there, but the hypotenuse being the second contact, you can design those prisms. So based on what they're made of and what their dimensions are, so that none of these light rays is actually capable of refracting back out into air. They're all going to be reflected completely on the interior of the prism. Then you can line up another prism so that you can force the same thing to happen again. And instead of bringing these light rays to focus at some point that is outside of the lenses, the goal here is to cause them to come into focus just ahead of the eyepiece, so that when you put your eye to the eyepiece, you're seeing a parallel light source. You're not just seeing, like, I guess it would be like one physical location where you see the moon or whatever object clearly, and every other position, if your head is a little bit too far back or a little bit too close, every other position would be blurry, which is not really what you want. You wouldn't want binoculars that are like so hair trigger that you have to know the distance between your eye and the eyepiece in order to see something clearer. So you bring it to focus a little bit on the interior so that you can put another lens here to turn it back into a parallel light source. So that means that you will be able to see that object to like equal levels of focus or equal degrees of focus if your eye is, let's say, 1 centimeter away from the eyepiece, or if it is 0.5 centimeter away from the eyepiece. You don't lose focus just by the position of your head relative to the eyepieces. And since you are like manipulating, or you're using total internal reflection here, you're not actually losing any of the energy of the light. The intensity is maintained because none of it is actually refracting back out into the environment of the inside of your binoculars. This is also exactly the same thing that happens with a fiber optic cable. If you want to like transmit some signal or some light source a long distance without losing any of the information or losing any of your intensity, you can just kind of feed it through a glass fiber that's arranged such that your angles of incidence are all too big for any of it to refract outward. And you can totally, or you could reflect internally and completely the light source until you feed it toward wherever the detector is. So you are, I guess this is sometimes used as a practical way to like put a bunch of components into one device, but still feed light from one point to the other, but not needing to do it in a straight line, if that makes sense. If you have like a telescope that's got let's say you're trying to collect light, you're trying to feed it toward a detector of some type. It might be like a literal CCD. It could be a diffraction grating so that you can take light and split it up the way that we did in our lab. The benefit here is that you don't need straight lines, or you don't need some combination of like straight lines and a bunch of mirrors, kind of like I think I mentioned the Michelson interferometer as it related to those failed attempts to determine what light passed through, but I didn't actually include an image. If anybody is interested, I do have an image of that. It's basically just causing a light source to undergo a whole bunch of reflections using flat mirrors. You can get around that by just using the boundaries of the fiber itself to capture this light source and feed it in whichever direction you are, whichever direction it needs to be so that it can reach this detector. Okay, I think, yeah, that's the last bit of our first half. So let me log back in here and we can solve example 2. So this is like another practical application of total internal reflection as it relates to cutting a gemstone. So a certain portion of what is it? There are terms that I learned in some commercial that are failing me, but there's like the concept of fire as it relates to how like brilliant or impressive a gemstone can look. It's got to do with the index of refraction of the material. Sorry, my other mic is on. Sorry about that. So it has to do with the index of refraction of material. It's got to do with how the faces on like the lower side of the gemstone are cut. And to a certain extent, you are trying to, or if you were the jeweler, you would be trying to force total internal reflection to take place so that you have more light bouncing around on the interior of the gemstone, so it looks more impressive from when you're viewing it from above. So a cubic zirconia has an index of refraction of about 2.18. We want to figure out what the critical angle is for that material. So imagine that you've got a light ray that originates somewhere outside of the gemstone, but it passes into the gemstone. If you are viewing this from above, then the critical angle would be the one where a portion of the light ray is refracted along the boundary, but it can't jump back out into air. The rest of it, the bulk of it, is just reflected back into the stone itself. So where is my stylus? Oh, there it is. Okay, so I'm going to flip over. Quit sharing here, start sharing on that side. All right. So we've got our materials, 2.18, and then n is equal to 1, so that we can find our critical angle. This is going to be the inverse sine of 1 over 2.18. And to maintain sig figs, I'm going to keep us at 3 here. We want to figure out what our theta c is going to be. It's as simple as just plug and chug at this point. So 1 over 2.18, if I take the inverse sine of that, I'm going to end up with 27.304 degrees. And to 3 sig figs, this would be 27.3. So all angles of incidence greater than 27.3 are going to result in the light being captured inside the gemstone and undergoing as many like total internal reflection events as you can achieve. The more you could achieve, the more brilliant that stone would look. All right, so let me quit sharing on this side, log out on that side, and we can use our last few minutes to look at the second half of this chapter. All right. Oh, okay. So the first part of that chapter was basically about kind of nailing down what the laws of reflection and refraction mean and the the conditions for total internal reflection. And the law of refraction is going to be the one that we kind of shift back to for the first half of this second part. So we're going to take a closer look at what actually happens to